my name is Ulrich Poschinger. So now we're going to switch gears a little bit and come to some experimental stuff. So as Ferdinand said, we are currently working on the realization of a heat engine based on a single trapped ion working in the quantum regime. So what we are normally doing with trapped ions to make a living is to do scalable quantum computation. So we have these microchip ion traps here in which we can move a number of ions around and make sure that only a given number of ions at a time is interacting with lasers which drive gate operations. Yeah, so we know very well how to manipulate qubit degrees of freedom and also motional degrees of freedom. So that's why it's of course obvious that it's a nice playground to start looking into heat engine ideas with these kind of systems. So there's already one realization of a single ion heat engine from our group, which was mentioned a couple of times. So here we have a tapered ion trap where the radial confinement is getting tighter in this direction here and more loose in the other direction. Yeah. And now the ion can be heated by injecting electrical noise to the electrodes. So it starts moving in the radial direction, and then because of this confinement gradient, it's pushed towards the right. Then a cooling laser comes in, which again removes energy from the system. The ion moves left again, and this way we realize a 4-stroke cycle. So this was the first realization of a single ion heat engine, where the working medium is a radial motion in the trap, the piston degree of freedom is the axial motion, and then there's different reservoirs. The hot reservoir is emulated by electric noise, and the cold reservoir by laser cooling. So this entire thing here is entirely off the quantum regime. It's macroscopic scales which we look at, and now the next obvious step to do is to look at the realization of a heat engine in the quantum regime. Yeah? So for this we changed the setting a little bit. So now the working medium, instead of a motional degree of freedom, is an internal state, namely an electron spin of a trapped ion. The piston is still axial motion in the trap, and now the cold and hot reservoirs are both emulated by optical pumping. So that's the basic setting. Yeah? We have an ion sitting in a harmonic trap. Additionally, we have an optical lattice. So that's the polarization lattice which does a spatially modulated AC Stark shift, which depends on the spin. So if an ion is sitting here in the node of this lattice, it's pushed to the left if it's in spin down and pushed to the right if it's in spin up. So now we just do alternating optical pumping, which is modulated at exactly the trap frequency. Yeah, so we pump between two different internal states, and this way we start to get some resonant excitation of the ion in this harmonic trap potential here. Yeah. So we can measure this time varying polarization. It's a spin polarization which varies with time. This is what you're seeing here. So that's possible that's characterized very well. Yeah, and then from this, that's messed up here. Sorry for that. To a spin polarization, we can just assign Boltzmann weights and come up with something like a temperature. Yeah. So and this temperature, because it's a two-level system, can range from 0 to infinity and then from minus infinity to 0 again. So we have to be a bit careful here with the analogy. So we restrict ourselves to this working regime here of positive temperatures to stay physically meaningful. Yeah. And this is a sketch of the realization of this 4-stroke cycle. So we alternately couple the ion to hot and cold reservoirs, and this way the piston gets resonantly excited. Yeah, so you can come up with a very simple model to describe this process. It's a classical equation of motion of a harmonic oscillator with an additional washboard potential, which is spin dependent, and the spin dependence here is in this random spin flipping process, which is characterized by these mean values here. So we can compute individual realizations by coin tossing, which is done in a way to make the average values consistent with these measurement values here. And then you see single realizations in terms of energy versus runtime of the heat engine. Yeah, so you see there's sudden kicks which pertain to spin flips, where due to a displacement in this optical lattice, the energy is suddenly changed. Yeah? And what you also see, because it's a single microscopic degree of freedom, this is subject to work fluctuations. And it's our goal to exactly being able to quantify these work fluctuations and to check if we saturate the bound which is imposed by the randomness of this spin flipping process. Yeah? So that's the experimental setting. That's a segmented ion trap, two laser beams forming this polarization gradient standing wave, a laser cooling beam, and then two additional beams which are used for analyzing the motional state of the piston. I'll come to that later. And then most importantly, we have the optical pumping beam coming from one direction, which is modulated by an electro-optical modulator to switch back and forth between two polarizations. Our measurement is done as follows. So we prepare both the piston degree of freedom by ground state cooling and the spin degree of freedom by optical pumping. Then we operate the engine for a defined amount of time. So this is done by having both the optical dipole force lattice switched on and the alternating pumping. Yeah? And after that, the spin degree of freedom changes its meaning. It's not the working agent of a heat engine anymore, but it's a probe for the motional state. So we just drive Jaynes-Cummings-like dynamics to map information from the piston back to the spin. We read out the spin. This is repeated very often, and from that we can reconstruct the motional state of the piston resulting from operating the engine for this defined time here. Yeah? So the optical lattice comes with a caveat. So unlike for neutral atoms, the position of the ion is defined by the electrostatic trapping potential. So in order to do something meaningful, we have to be able to place an ion at a well-defined location within the lattice, yeah, at a node or an antinode. And as the optical phase is drifting in a realistic experimental setup, we have to do some feedback. So we do additional measurements all the time where we measure AC Stark shifts induced by the lattice, yeah, and from these values we feed back on the ion position to keep the ion at a well-defined place in this optical lattice. And then we can quantify how well this works by doing a Ramsey experiment. So we just create a spin superposition, let it pick up a phase in the lattice and probe the spin after some time. So this is what you see here. Yeah, that's the spin polarization value versus exposure time to a standing wave. That's for emotional ground state, the upper panel, for three different locations in an antinode, in a node, and somewhere halfway between. So here at the antinode, you see that the rotating phase, yeah, so the spin superposition picks up a phase. And here at the node, you just see dephasing. So there's no AC Stark shift at the node, but the lattice is still somewhat shaky. So the superposition is dephasing here. Yeah? So from this, we can compute the jitter of the standing wave. That's a small fraction of the wavelength, but the question is this good enough to get this heat engine principle going? By now we know that this piston is subject to resonant excitation and some randomness. Yeah, so obviously the workhorse for its characterization is a displaced thermal state that's just defined by having a displacement operator acting at a thermal state. Yeah, that's a thermal distribution. The nice thing about that is also that the corresponding passive state is it's just given by the thermal state. And then from computing the Q function, which is Gaussian, we are able to compute moments of the energy distribution in terms of the displacement parameter beta and the thermal Phonon number n bar. So that's all we need to know. And for characterizing the work fluctuations, we're just interested here in the second moment of the energy distribution. So now how do we probe the motion? What you see here is a familiar ladder scheme for a two-level system ion with a harmonic oscillator degree of freedom. So we can drive various kinds of transition in the system. A carrier where the Phonon number is not changed, red sideband transition where one motional quantum is removed from a pi flip. Yeah, then conversely for a blue sideband, one phonon is added. Then there's also the second red sideband and so forth. And the cool thing about this is that for all these transitions, the Rabi frequencies depend on the initial Phonon number in a nonlinear way. So, and this exactly provides the information upon driving dynamics about the motional state. Yeah? So, what you get from driving the spin on one of these specific delta n transitions for time t is a superposition of Rabi oscillations at different Rabi frequencies, which are weighted by the corresponding phonon number distribution. So from monitoring this observable signal here, you get information about the phonon number distribution. In our case, this phonon number distribution is parameterized by exactly these two values of interest, namely beta squared and n bar. Yeah? So here's a couple of examples. One state close to the ground state where the carrier and the blue sideband are flopping and the red sideband hardly doesn't do anything. Then one state with a large thermal excitation where the oscillations are predominantly on the sidebands, and one state with a large coherent excitation where we even see flopping on the second red sideband. Yeah? So the scheme is we monitor these kind of signals here, we reconstruct the phonon number distributions, and from this we infer the thermal phonon number and the displacement parameter. And that's the result of running the engine for this time here. Yeah? So here we plot the coherent and thermal phonon numbers, so this doesn't yet look so meaningful, so we just compute the energy statistics from that. So here you see the same result expressed in terms of mean energy and energy standard deviation. Yeah? And along with that, we also plot average values from this very simplistic Monte Carlo type simulation. Yeah? And the cool thing here is that surprisingly, we were really actually close to saturating the bound imposed by the randomness of the optical pumping. So the performance of the engine in terms of work fluctuations compared to mean energy is actually quite good. Yeah? So unfortunately, that's not the whole story. So the question is the description in terms of a thermal coherent state actually fitting? Yeah? And not always, because we have an anharmonicity in the problem, namely the optical lattice. So after like larger runtimes here, if you look at a computed phase-based distribution from the Monte Carlo simulation, you see that there's, due to the anharmonicity, there's also phase dispersion here, yeah, along the circle, and this circle here would correspond to the fit for a thermal coherent state. Yeah, so. To be able to figure out everything about the state, we have to get the full information, and this we can do by measuring the Q function. So the Q function is nothing else than the vacuum amplitude corresponding to the original state which we want to measure, and which is displaced in phase space. Yeah, and this is actually accessible to measurement. So this has been pioneered by Ki-Wan Kim's group. So the principle here is that of course we're just able to do a displacement operation by means of an electrical kick. And then we have access to the ground state occupation probability by doing a robust population transfer on the red sideband. So all the population from n equals 1, n equals 2, and so forth is shelved to spin down, and only the population corresponding to n equals 0 stays in spin up. So this way, by measuring the spin, we have access to this quantity here, and then we can just change alpha to reconstruct the entire Q function. So this is already sort of working. Yeah? So the scheme here is again preparation, run the heat engine, then do a couple of electrical kicks, which are spaced exactly by the trap period and spaced with respect to the heat engine operation by a delay which defines the phase here along the circle. Yeah. And this way, for testing it for the ground state, we get this kind of Gaussian here, along with a nasty ring. The ring is due to the fact that for higher exciting states, the coupling on the red sideband becomes again very bad. But I think it shouldn't matter so much, because the interesting dynamics is going on in this regime here. So here the scan range was just too large. So that's what's currently going on. So as a conclusion, we have demonstrated a single ion heat engine, which is now operating in the quantum regime. We have access to work fluctuations. The questions to be addressed is still how close are the work fluctuations to the ultimate bound if we take these phase and enharmonic phase fluctuations into account. That's just the starting point, of course. There's a couple of extensions in the future we want to do. So we've been only looking at the onset behavior of this heat engine. Of course, for applications of heat engine, we're interested in limit cycles. So we have to add some dissipation. Yeah, so this can be done by adding some additional cooling beams and trying to achieve limit cycle operation of the system. Then also what would be interesting is would be going from the Otto engine to a diesel type of engine, which is autonomous. So in this case, we could just add some additional resonant optical lattice with the polarization gradient, where like position fluctuations would also lead to self-excited spin pumping. Yeah. And finally, the ultimate thing to go for would be really to have ions also acting as actual reservoirs of finite size, and we could move the working ion back and forth between these reservoirs and have it interacting either by some laser interactions or just by Coulomb interactions. Yeah, and this way we could ultimately realize heat engines which operate while not being looked at. Yeah. All right, that's the team. So David and Oliver have been taking and evaluating the data. Christian Schmiegelow has contributed a lot to the setup, especially he got the standing wave going. He now runs an ion trap lab in Buenos Aires. And Erik and Alex are doing the theory work for this project. Thanks a lot.
Questions? Yeah. How do you know you're in the quantum regime? What is your definition?
What's the definition of the quantum regime? So I was talking of phonons. That's my definition. So it's I'm not calling this a quantum heat engine, yeah, but it's starting at the ground state. Perhaps that's a good answer. Yeah, we are starting at the ground state.
If I may, you run the regime in a temperature with the discrete spectrum of 2 levels. You see the discrete spectrum of the engine and of the oscillator, which uses a piston.
Fantastic. It was very clear, the talk. But if there are questions, there's a question.
So the standing wave for the calcium ion, is it so optical lattice?
Yes.
What is the polarizability of calcium first?
So we're normally not talking about polarizability. So what's interesting in the end is the AC Stark shift, right? And that's a couple of megahertz. So it compares well to the spacing of the harmonic oscillator levels.
I think I need some details. So can I think of it as a adiabatic autocycle? Or
I would say so, yeah. Yeah.
Any chance to probe the non-adiabatic aspect of it?
Yeah, so that would be also a nice extension to go for super adiabatic engines, yeah. So it's definitely something to think about.
So why did you need this additional coherent wave?
So, I mean, there needs to be some coupling between the working agent and the piston, and that's exactly provided by the standing wave, yeah. Otherwise, it would be two fully decoupled systems.
But maybe one can answer also the question, when you, in the sense that the analysis of this engine is fully quantum. Okay, the operation is not deviating from, or we don't see immediately where to deviate in its operation, but its analysis is fully quantum. So we have the full tomography of quantum states of motion and also the full knowledge about the polarization. So there we can write down the full quantum state that is at any time of the operation in the machine. The operation itself, that's a question. Okay, there I don't see immediately that there would be a difference, but what you see is that this optical pumping events, they are the dominant, or according to our measurements, they are completely overwhelming the fluctuations. So that is a very genuine spin system which is either up or down, and that is dominating the fluctuations in the whole machine. So this fluctuation part may give a hint that this is really in fluctuations dominated by something which you easily explain in the quantum language. So,
well, you can do the dynamics of the planets with a quantum description, but
yes.
the question is it necessary to understand some features?
Yeah.
And that's an open question.
So there are
somehow I'm afraid that this is not fully autonomous because you have this modulation of this pumping, which is in resonance with. So this is not a 100% heat engine, which would rather involve some constant supply of
it's
of
like
work,
a
kind of self-oscillation.
like an engine where you inject fuel periodically.
Yeah, and what is important, the same frequency as the operation of the piston.
Exactly.
So
That's
it's-
why that's the next logical step is really going to autonomous operation.
But maybe you can go back to this and show exactly how it will work.
Yeah. So there would be an additional lattice which would be resonant, also have a polarization gradient. Yeah. So if the ion is moving along the axis, it's also it's scattering to different spin polarizations.
Because we have rather general result that if you start with a ground state or any passive state, you cannot generate work. You need a kind of initialization of the state of the piston. So you have to put first the shift. I think this is probably played by this external periodic perturbation.
So you have the ions to start here, and then you get some certain polarization, which gives you then a kick to one
The initial
side.
kick, yes.
And then this
is necessary
initial kick
somehow.
will lead to another position in the optical pumping wave, where the polarization is different, the temperature then different, so to say. So where it was here cold, it's there hot, and then it drives it back. And now it becomes self-oscillating. That's the autonomous version which we have.
So it's really interesting. Yeah. So probably you have to start it, like you have to start the engine in your car, but probably it's enough to have quantum fluctuations, which starts this kind of engine.
Probably, yes. But this
I don't think it's enough to have just quantum fluctuation, because, sorry for using the dirty word, but you have to make sure that it's initially non-passive. Okay, and if you just let quantum fluctuations operate, it will be an initial thermal state.
It's not enough.
Yeah,
You need some
it will be an initial thermal state.
deterministic
That means you have to avoid.
initialization of this.
Yeah, you need to give it an initial mean amplitude. Okay, without the mean amplitude, it will not be able to produce work. Okay.
Okay, so thanking all the speakers of this morning again, and we recently, after lunch break, as announced in the program.
Yeah, we're going to have a very large lunch break, but maybe make a short announcement, because today we have to relinquish
I know it, but
this room for during the lunch period, which means that you cannot leave your bags here. A lot of you, I know, have your luggage here. So I would suggest that you bring it to ITAMP,